Hi and welcome to another episode of Fika Chat about the future of education. And today we're at the exhibition, the poster exhibition here in Micro and Nanotechnology, the Department of Micro and Nanotechnology. And we will have a look at some of the posters, and we actually have to be a little bit careful because some of these posters they are buying for patents, so we cannot record everything. Hello, so I am here with Valentina, and you are getting ready to do a little poster
session.
Yes,
yes.
Nice.
We are in Micro and Nanosystem division, and with today it's our internal poster session, where every year it's annual event for the department, and we actually make one minute pitch all the students and the people that they present. Actually, we are PhDs or postdocs or master students, and we are presenting our research in posters. So in the corner up there, you will see the posters, and it's actually very nice activity every year. We just do it, and it's very nice engagement. We learn about each other and about the research, and sometimes it leads to nice collaborations.
Oh, very nice. Yeah, and it's kind of a informal setting, but you said it's actually kind of formal.
Actually, it's informal, but I mean, we do as in conferences. We have the pitch, and we have actually a prize for the first pitch.
Good.
Yes.
Yes.
And then we have a time that we stand by our posters, and we just discuss with our colleagues and explain and new things, maybe unpublished sometimes. So yeah, it's really good.
And then you can give feedback to
we give feedback, or it's nice. Maybe sometimes we make a small projects, we collaborate afterwards. It's really nice. It's really nice engagement. For the department.
And I noticed that you have a little QR code as well on each poster.
Either with contact details or project. Actually, I forgot to put mine. I remember. Yeah.
So then you can give feedback to each other also afterwards.
It's really nice. Really nice. Yeah.
And how many years have you been doing?
I think 7 years.
Oh, nice. Nice. Yeah.
I'm here the 4 years, I think.
Yeah. And today, can you give us some
my research is about
your presentation?
Sensors that they call solid state nanopores, and we use them for sensing molecules or DNA. So come to my poster to see.
We will. Yeah, thank you. Looking forward to see the poster presentation. I also had a chance to meet with Thomas Winkler, who actually started the poster exhibitions a few years ago. And now his initiative is what made this whole format possible. Let's listen in to Thomas and what he has to say.
So it's to give everyone a quick overview of what will be happening. And I think we've tried out different lengths of the pitches between 30 seconds to a minute so that it doesn't run too long, but so you still get a brief idea of what people are doing. And then the poster session runs longer, so you actually have time to talk to the people. And for that, it's important to make sure that everyone has an opportunity to talk to the other people. So the poster scheduling actually gets a bit tricky, that everyone is there at their poster but can also talk to everyone else.
Excellent. Thank you. Very nice talking to you.
Thank you.
Good. And now we will listen into some of the pitch presentations that are taking place just here behind me.
The objective of this poster session is to know each other's research within MSD. And here is today's schedule. So we are right now in the middle of the introduction. So after the introduction, we will move on to the pitches. Then from 2:30, we're gonna do a poster session. There is a bit of margin between the end of the pitch and the poster. So during that time, you can see around each other's posters in the corridor, and make sure to hang your poster by 2:15. And after the poster session, we're gonna have a closing and our ceremony. Then from 6:50, we will have a dinner at Restaurant Noi. And here is the timeline for the poster session. You can also find this information in the email that I sent yesterday, and also you can find this real-time information on the header of your post in the corridor. Okay. Then, of course, we have some prizes to recognize your effort. And there are 2 prizes, one for best pitch and one for best poster. And each winner will receive 700 SEK this year. But now we start with the pitches. I remind you that you have 1 minute for the pitch. So we have timed already the slides. So after 1 minute, it will move forward. If you do less time, then I will manage to it.
Schizophrenia is one of the top 10 causes of long-term disability, yet there's still a lack of curative therapies. And one of the reasons of this is because we don't fully understand how the disease begins and progresses yet. So, in this project, we're addressing this gap by using patient-derived stem cells to build a schizophrenia-specific miniature brain on a microfluidic on-chip platform. And what makes our system truly unique is its real-time closed-loop feedback control, combining electrochemical sensors and controllers to continuously monitor and adjust the biochemical environment inside the chip. And with that, we'll be able to study the dysregulation of reactive oxygen and lack again species in schizophrenia and hopefully identify non-therapeutic approaches. Thank you.
Sure. Yes, no.
So in my project, I make waveguide integrated graphene detector. And it's waveguide integrated, so you are supposed to illuminate the detector through the waveguide. But when I illuminate the detector from top, I get like unexpected result. And I publish it. I get accidental publication. So if you want to know how I get this accidental publication, come to my poster. Maybe we will figure out some accidental business.
Hi everyone. So I'm gonna talk about solid state nanopores, which are basically tiny holes on silicon nitride or hafnium oxide film. Imagine 5 to 15 nanometer. And in our project, basically, we're focusing on finding different fabrication methods, repeatable and scalable. And also we are performing a DNA sequencing data, but also a nanoparticle trapping. And we have a very nice result that says that maybe this membrane can work as memory store. So if you want to know more, come to my poster too.
And now I'm back with Mina again, who will talk us through her project and her poster. So I'm here with Mina, and I remember something from your pitch. You said that you were building a schizophrenic brain. Am I correct?
Yeah, it's like a mini brain model.
This is fantastic. Tell me, how are you doing?
Yes, so since schizophrenia has a genetic cause, but also environmental, we can actually derive stem cells from schizophrenia patients. So you can just take like skin cells from a schizophrenia patient, which is very easy to get. And then you can reprogram these cells to turn back to like an undifferentiated state, and these are then called induced pluripotent stem cells. And these can then be differentiated towards any cell type that you want. So since schizophrenia affects the brain, we want to differentiate them towards all the different cell types of the brain and the blood vessels on the brain. And this way we want to develop a model. So actually it's the chip that's the main model of the project. We want to build a very tiny model of the brain so we can mimic the different compartments of the brain. So we have the endothelial cells here that mimic the vasculature on your brain. Then we have the perivascular compartment, which is around the vasculature, and then the brain compartment, so the neurons in your brain and the other cell types.
So this is basically the artificial schizophrenic brain.
Yeah, exactly. There's also a more simple model over here, the transwall culture. So then you just have these plates with wells in them, and then you can culture your cells in there, and then put these little inserts that have a membrane here that still allows for communication between the cells in them. And this way you can also create a model. But here we want to show the advantage of having a more advanced model compared to the transwell cultures. So we will, in the first step, so differentiate the cells, make our chip models, and this is actually this one as well, compared to the transwell cultures and compared to human samples of schizophrenia patients. Yes, so we will get blood samples and cerebrospinal fluid to see what's happening, like peripherally and in the brain in schizophrenia patients, and compare it to the brain models and see which one resembles the human samples the most.
And the overlying aim or maybe the underlying problem is that schizophrenia is very complicated. We don't know exactly what causes schizophrenia. And using these kind of artificial brains, we can hopefully understand more about schizophrenia.
Yeah, exactly. Because previous research has mainly been focused on neuronal dysfunction. So you're only focusing on mainly one cell type and not really looking at interactions between the different cell types of the blood vessels on the brain and the other cell types in the brain. And we want to broaden this and really look at interactions between the different cell types of the neurovascular unit and find causative roles of certain cell types in the development of the disease. So we just want to get a more broader understanding of the mechanism of the onset and progression of the disease. And if we get that, then hopefully we can also more easily find a curative therapy, because now schizophrenia patients just get antipsychotic treatment. So it doesn't cure it. You can just reduce the symptoms. So hopefully this will help with it.
Very interesting. And is this your first time you're doing this kind of pitch session?
Yes, indeed. I recently started, so it's my first studies.
Interesting. How did you find out about KTH? What made you apply for a PhD program at KTH?
So I was actually here in Sweden many years ago for an internship. I was at KI, and I really liked it. So I decided to come back. So I did my PhD then in Belgium, and then I decided to come back to Sweden for postdoc.
Oh, very nice. Oh, so you're doing your postdoc now?
Yeah.
Yeah, sorry. Yeah, you're doing your postdoc.
Yes.
Yeah. Thank you so much. Very interesting work, and good luck in the future. Yeah. And now I will meet with Henar Marino, who has been part of the organization for this event, and we will also listen into her presentation of her poster. Hi, I'm here with Henar, and you are organized this event.
Yes, I'm one of the organizers. Yes.
Nice. How many times have you been organizing this pitch event?
3 or 4. I think this is the 4th year. The first year I was involved just to kind of learn the process. Then I had, 4 times. So 2 years where I was the lead organizer, and then this year that I'm kind of teaching some other people.
And do you want to do a super brief presentation?
Yes, of course. So basically, the main idea is that we're trying to speed up the diagnosis of sepsis. So I don't know if you know what sepsis is, but basically is defined as a life-threatening organ dysfunction that you get when you get a very severe infection. So your body is overreacting to this infection by basically shutting down organs and so on. And it causes a lot of deaths globally, so it affects a lot of people, and current diagnostic methods take a very long time to yield results. And one of the reasons for this is because you can find very few bacterial cells in the blood. So what we're trying to do is speed up that diagnosis time so that we can detect the bacteria earlier on, and then we can give the patient or the doctors the data of okay, do we have bacteria in blood? Yes or no. So we want to have a detection assay. And then we also want to know what bacteria is causing or what pathogen is causing the infection, so that the doctors can then adapt the treatment to give the patient a personalized treatment. So in a very few words, that's sort of what we're doing.
Amazing.
Yes.
I spoke to Walter before, and he said a lot of these research projects actually lead to kind of real companies.
Yeah.
Which phase would you say that this research project is?
So unfortunately, I don't have a second poster with my colleague Mohammed, but so this was this was sort of the proof of concept that we can actually separate the bacteria from the blood and put it in a device where we can actually see it and we can see the bacteria growing. Like you can see it here, how they we trap them in a micro channel and then they start dividing and growing and so on. So this was sort of the proof of concept. And then that we can do this with just a centrifuge, right? And then my colleague Mohammed, he's built a device that does all these manual steps, like here up to number 3, in one single device. So that's what we were trying to commercialize, because this is a lot of manual steps, unfortunately, but it was a very solid proof of concept that, okay, this is feasible from a physical perspective. And now Mohammed is building a device that we can actually commercialize and sell. So that's what we are aiming for. So for this protocol, exactly, I think we're far from commercializing it, just because if you try to put something in the clinic that has so many manual steps, this is not going to work, because the nurses are already overwhelmed. So they cannot spend 5 minutes per sample to prepare it. You need to give the doctor something that they can just put their sample in, put it in the centrifuge, and then get a readout, basically. So that's what we're trying to commercialize. So this was kind of proof of principle, and then we have another device that we hope to commercialize. I mean, yeah.
Again, I said it so many times today. So sometimes you have this specific technology, and it's very applicable. This will lead to
hopefully, yeah, exactly. Yeah, I think that's what I always say, that sepsis, it's really a fight against time. So that's what we are trying to save on, is time, because time is what's going to save lives down the line. So that's what we're trying to solve. It's a time issue. Yeah. Absolutely. Absolutely. Yeah. So it's there's a lot of companies. Obviously, it's also kind of a race with all other companies. There is so many people trying to work on this and get a product that works and is the first one in the market. So it's a very complex problem.
This have competitiveness, isn't it good stress?
Yeah. I'm not super stressed. For me, if anyone finds a solution for this, I would be super happy. It's not that I feel I need to be the first one from a competitive point of view. If anyone manages to find a cure for this, or not a cure, a solution for this, I will be happy to go work for them. So it's, I think that's a little bit more the spirit in Sweden.
State of the art research.
No, it's super exciting, and as you said, it's very applicable. You can, from the poster, from the research, you can see the real world application that this has, and that was for me very important. Choosing a PhD, and when I discussed with Walter, that was really something that I was aiming for, to have a project that is not. I think basic science is beautiful, but for me, I wanted to work on something that could hopefully help someone. So
how about you choose KTH as your?
But it was not really choosing KTH. Walter had this very beautiful project, and then I saw it, and I was like, "Wow, this is my dream. This is what I want to work on." And then I applied, and it was a good match. So I got the job, and then I was like, "Okay, Stockholm sounds great. So let's go." And
where are you from
originally? I'm from Spain.
Is it?
Yeah. So I was a little bit afraid of the cold, but you get used to it.
You don't feel like it.
But then, of course, KTH is a wonderful university, so then it was an easy decision for me.
What do you think about the atmosphere here right now? Portsmouth?
I really like it. I think it's I think it's very department specific, but here there is very good environment. Everyone always tries to help you. I think also the Swedish culture really translates generally to Swedish universities. So you don't feel when I talk to my colleagues from maybe other universities, everyone is I'm working 20 hours a day. I'm I don't think here, of course, you can do that as well, but you don't have the pressure, or I don't feel the pressure from the PIs or the upper management at KTH to do this. So I think happy PhD students work better. So
still do this is a proof that you can still do
yeah. I mean, of course I still worked a lot. I don't mean to say I didn't work, but like, but I felt like, okay, you're working in an environment where you're very supported.
I kept talking to Henar Marino for a while. We had a very nice discussion and interesting talk, but unfortunately, we are out of time for this episode of Fika Snack on the future of education. Of course, if you want to know more, contact the Department of Micro and Nanosystems. Next, I had the chance to talk a little bit with Wouter Metsola, who is a professor here in Micro and Nanosystems. And his research focuses on actually many things, but some of them are nanostructured soft matter, biosensors, and biomedical micro devices. And we talked a little bit about some projects that have made a journey from research to innovation and then gone all the way out to the market. Let's hear what he had to say.
We work very often together with KTH Innovation, actually, because they're really good at this. And they know us very well. We're one of their best customers. So we go with an idea. Like last 2 weeks, for example, we have a new idea on carbon capture. And then we invented something new that can do this super efficiently. And we go to KTH Innovation, and then they help us with some first funding to do, patentability search and then maybe make a market report to see, how this looked like. And we use this to understand, because we have something, and how to bring this further. We need to understand, should we go hand in hand with a partner, or should we build our own company, and how do we protect our IP? And this is something that you really have to think about from the start, understand if I'm going to end up in technology that is a level 4, which means I can show it works in my lab. Next level is I can show it works in a real environment.
Okay.
So, for example, with this one, the first thing we showed, we can use this in, we can test this, we buy a stomach from the slaughterhouse, and then we work on it, or an intestine, and then we work on that and say, hey, this works. But then the next is that you go to real and you test on real animals, and then in a real setting, for example. So you have to take step by step.
And just explain this this lucky loop. You explained it in Swedish, but explain it just briefly.
Yeah, so what lucky loop does really is it helps sampling cells, and this is something many medical problems can be diagnosed if you have access to specific cell samples, and you can look at how does a cell look like. How does it behave? For example, is it cancerogenic or not? But that means you need to be able to pull out these samples. And for example, a very easy way to pull out samples is when, for example, if you have a spot on your skin and you say, is this cancer? Then they will take a biopsy. And then they can test. If it's a swab, for example, often you can take for DNA, they take the swab from the inner chin, because that pull out cells and then look at it. But there are places in the body that are very hard to reach. We call them hard to reach places. That's what we call it. And in this case, there's the pancreas. We have also technology where we focus, for example, on the kidneys or outer lung or the brain. You can go in with, go all the way to the brain if you go via the bloodstream. So we go either via the bloodstream, we develop technologies for the bloodstream, and we develop technologies via the mouth.
All right.
And then there's other places also you can go, but those we have developed. And this specifically one lucky loop is really for via the mouth go in. And this is when you see on an ultrasound that there are cysts in the pancreas. Very often they are benign, you shouldn't do anything. Most of the cases, actually, way over 90% is totally harmless. But you want to know if some of these cells are potentially cancerogenic, and then you want to harvest the cells. And what you can do is stick in a needle, so you can go via the esophagus, down in the stomach, and then through the stomach wall into the pancreas and suck out the cells with a very fine needle. You don't feel that. Patient is asleep, you just stick in, take out cells, and then do the test. But the problem is that often you don't get good enough cell sample, or you don't have enough cells. So what we are developing is a little brush that you can actually push to this very tiny needle. The needle is less than half a millimeter. They push this brush to this needle, and when it comes out, it can brush out the cells that are on the inner wall of the pancreas, fall in the liquid, and then we suck them out, and then we can show we have 10 times more sample that way than normally. So then we can diagnose also the cases that are actually, without sex.
And you said this was it was a PhD student who started this
Yes,
project.
all of these are students.
Is it PhD student? Yeah. And they are now
Companies. These are all
real companies.
For example, Mercine Lab is a company that's totally, they have their offices on campus, but they are standalone company for many years already. And it's a company, 6 persons working there full time. They're developing coatings for fluids nowadays.
Okay.
This is not what we started. They started in my lab at some point. But this was the stuff for making diagnostics, and they needed specific plastics polymers. And we developed those, and then these are really clever guys. Let's make a company around that, but very soon they understood that the big market for this kind of molecule is like flooring, it's an extremely good material to put any paint on any surface. So then we went into that market, and that's what they're doing now, making coaters. So you see, things develop very differently, and that's always this. You start with a PhD, but you don't know what you're going to get out. The same with the carbon capture technology we're developing. We started as a lateral flow test also. We were trying to make the COVID test. You have the sample that flows, and you try to find molecules. We made specific structure. We did that could do that very efficiently. And our students said one day, you see what? If I put my droplet on top of the structure instead of on the side, actually it was true, but it creates small droplets. Very regular array of droplets. And we had never seen that. We didn't know of any technology. So you have a material, if you push to a liquid, it will self-organize in tiny droplets in very specific points, like in square cubic lattice. Hundreds of thousands of these droplets. Very just push the liquid and poof, you have an array of droplets. This had never been done. So the first, we published this in Nature Physics because it's a statistical principle nobody has ever seen. And the second thing is, I think, what can you use that for? And at the time, we were developing, we can package cells, therapeutic cells for cancer treatments. And this worked. But then I figured out, this is going to be 10, 15 years research just, to bring this in. And the amount of money you need to bring this forward is too much. I can't handle that. And then I kind of, I thought I let it go, but I had a partner at the same time that helped me. He thought, let's try this for other technologies such as, capturing carbon or.
Interesting.
And so and then he tested, and it showed up to be fantastic fuel for that. And it solves a lot of problems that we actually didn't know they had, but it's,
And then you find out new solution.
And then when you start thinking, that's what we're doing. What we done last week, thinking okay, how do we change this to actually, turn this into real products? And that's I can't tell too much about that. There's a lot of work thinking behind.
Yeah, that's your conditions.
So it is
really
research.
Fantastic. Yeah.
Nice.
Yeah, but it's good.
Yeah,
it is. What was this again?
This is bankrupt already. This went all the way to Nasdaq many years, and then it went bankrupt. This is a fuel cell. So the idea was we invented this 2005. So this little puck you see, this power track, it's basically what is salt. And if you put this in this green stuff and you add some water, it will generate enough electricity to load your phone on load.
Okay.
So it's kind of, maybe 10 pucks with you when you go camping. And then, every time you need to load your phone, you put in a puck, add some water, and then you load your phone.
This is perfect, yeah.
Yeah, but
go bankrupt.
That is a question of marketing and finding the right market for the right product. And this is not research. This is, all we can do is, what I can do is bring this to a point where it becomes commercialized, and then find a market, and there are other people that do that. They started developing technologies for loading cars using hydrogen.
All right, yeah.
So because it was the same type of technology they needed, and I'm not. Then I was not involved in it. It was successful for a while, but then this market is very volatile. It didn't work out. It happens.
So interesting to see that. It's like having your kids and see how they're doing in the real world.
Yes.
Fantastic. Yeah,
but this took a journey actually. We had to learn, especially in the case of medical technology, that you have to sometimes start your own company and to think from the beginning. And this is something we really need to learn. We didn't know that. Well, we didn't have that education before, so we did this bit by bit to figure that out. And especially Niklas Rockstedt and myself that works in medical technology, that had to learn to think that way.
Okay.
And now it's the systems, when a student comes in, because around here there's 4 CEOs running around you, and this already at the moment, yeah. So people that are either still doing research or that that are already CEO, but are still they're still part of research that work along. and they're training new people that then do their research here. And so this is an ecosystem for people to, people see how it's done, and you get inspired, and you also understand what you can do and how it's done. And
yes, it's really building a process for
it's about building process and understanding how the workflow goes. And this is specific. With our research, we can do that. There's other research, like if I go down one floor, they work with signal processing, which is basically mathematics. This is not, this is not how they work. They eat, they feed into, other companies that need their mathematics, or they have different ways of creating impact. But this is how it works. It's very visible, so it's easy to show on the camera. That's
a very nice thing. Yeah, I love this kind of system that integrate with your body as well.
Yeah.
It's like this kind of cyborg system. Now we have seen some pictures and some beautiful posters here at the Department of Micro and Nanosystems. I have learned a lot, and I hope that you all have learned a lot as well. And if you want to know more about how to set up a little presentation like this, or do an exhibition, a poster exhibition, you can always contact Framtiden at kth.sc, or just contact the Department of Nano and Micro Systems. And of course, I know Sophie always reminds me to remind you that please follow us, subscribe to our channel on Spotify, YouTube, and listening to us on KTH Play. Until next time, have a good time. Bye-bye.